Good afternoon, everyone. Our analytical technique for this presentation is NMR spectroscopy. Nuclear magnetic resonance spectroscopy, abbreviated as NMR spectroscopy, is an analytical technique utilized by analytical chemists to determine and deduce details pertaining to a compound's magnetic properties. It achieves this by recording the magnetic spectral patterns given off by the nuclei within a sample's atoms. Organic and analytical chemists use NMR to ascertain the molecular structure of an unknown compound. The NMR spectrometer is used by these scientists to attain their desired NMR spectral data. The instrument processes its data utilizing electromagnetic radiation such as radio waves. The NMR spectrometer is able to pulse these electromagnetic radio waves at the unknown sample that is under investigation. The radio waves cause the excitation of the atoms present in the sample. These atoms will resonate at specific frequencies and produce a signal on the monitor of the instrument. The signals that are produced will be specific to certain types and groups of atoms and varies depending on the arrangement of the atoms that are bonded. The outputted frequencies detected by the NMR machine will be specific to each molecular structure present in the sample. This information is used by scientists to determine the molecular composition, and this technique is mainly used in structural elucidation. Each singular atom produces sufficient resonance shift to be traced by NMR machinery, and this is greatly dependent on and affected by the effective magnetic field at the nucleus. This resonance changes as an atom forms more connections with other atoms. We can draw upon these resonance patterns to begin to understand the details of a molecule's 3D structure and the functional groups that form it. The guiding explanation behind NMR is based on the phenomenon that nuclei possess two unique properties. The first is their ability to spin, and the second being that they are charged. These properties cause nuclei to react to a magnetic field. If we were to run an electric current or apply an external magnetic field, this would allow an upward energy transfer to a higher state. This energy transfer is reflected at a certain wavelength and radio frequency. Once the spin returns to its baseline, the emitted energy from the drop will be read by the NMR machinery. Likewise, the application of an external magnetic field can cause a nucleus to either spin in the same direction or against the direction of the magnetic field. A nucleus with the opposite spin will have higher energy. A nucleus spinning in the same direction will have lower energy. Additionally, the resonant frequency as it applies to NMR spectroscopy will be affected by a phenomenon known as electron shielding. It is known that the more electronegative the nucleus is, the higher the resonant frequency observed. The more electronegative or electron withdrawing a group is, the lower the chemical shift. On the other hand, the most electron donating groups will have the highest chemical shifts. The rise in chemical shift can be due to many factors, including the delocalization of current that occurs in aromatic groups that can distribute current across the groups. The following diagram is a labeled schematic of an NMR spectrometer. When interpreting NMR signals, there are four important factors that must be taken into consideration. 1. The number of signals will represent the number of equivalent protons that are all in the same chemical environment. 2. The intensity or size of the signal will be used to obtain a ratio of that specific type of proton. 3. The position of the signal will provide a chemical shift where the position of the peak in the NMR spectrum will indicate how de-shielded or shielded the proton is. And finally, 4. Signal splitting will be represented by the number of peaks or lines that a proton signal will split into depending on the other proton neighbors. The process of signal splitting is an important concept in NMR and gives us vital information about the protons in our molecule. This signal splitting phenomenon is one where we see a proton signal will split into several smaller peaks, all dependent on their hydrogen neighbors. Electronegative groups remove electron density and are de-shielding and tend to move NMR signals from neighboring protons further downfield to higher ppm values closer to 10. Electron donating groups pushes electron density onto the nucleus and thus has a shielding effect and moves NMR signals upfield to lower ppm values closer to 0 or TMS. When adjacent hydrogens are absent, only a single peak will be obtained. However, if one hydrogen is found on an adjacent atom, this will result in the resonance to split into two peaks known as a doublet. When there are three hydrogens on the adjacent atom, we will see the resonance split into four peaks, which is known as a quartet. The NMR resonance will split into n plus 1 peaks, where n represents the number of hydrogens on the adjacent functional groups. The number of lines observed for a given group of protons at a specific d value is called a multiplicity. The most observed patterns have been given descriptive names such as doublet, which is two equal intensity signals, and quartet, which is a set of four signals with intensities with ratios of 1 to 3 to 3 to 1. The line separation is always constant within a given multiplet and is called the coupling constant, known as J. The magnitude of J is usually given in Hertz, and it is independent of magnetic fields. Similar to other analytical techniques, NMR has been applied to various disciplines of scientific research. Such areas are material science and structural biology. Solid-state NMR can be useful in battery research. The goal of NMR analysis is to gather information associated with chemical shifts and spin lattice relaxation times to obtain information about phase chemistry, local structure, and ion dynamics. Using solid-state NMR to analyze battery materials is a very convenient way to obtain information. NMR is used to obtain battery materials because NMR spectra of lithium-6, lithium-7, and sodium-23 are impacted by the materials being analyzed because lithium and sodium ions participate in the redox reactions in batteries. NMR spectra of other isotopes such as hydrogen-2, potassium-39, and oxygen-17, quadrupolar nuclei where their I value is greater than a half, can be useful because these nuclei are found in different parts of an electrochemical cell. This allows for knowledge on short-range local structures to be obtained. There are challenges to analyzing these nuclei, however, because the quadrupolar coupling is large and the gyromagnetic ratio is low, which influences the detectability of the NMR. Information on ion dynamics, such as activation energies, can be determined by using NMR along with other analytical techniques such as impedance spectroscopy. Structural biology is another scientific discipline where NMR can be applied. The analytical technique is used when studying ribonucleoprotein, or RNP for short, complexes. NMR was only considered useful for smaller proteins in the past, but after the technology of the instrumentation has evolved, NMR has been proven to be useful for elucidating the structures of high molecular weight RNP complexes. The methyl groups of RNP complexes and the labeling of side chains of deuterated proteins has made NMR applicable to these RNPs. However, the use of NMR to investigate RNA, which is ribonucleic acids, is being further studied and developed as it will require even more advanced instrumentation. Ladies and gentlemen, I'd like to take this opportunity to thank you for giving me your undivided attention.